When I think about a revolution, I think of this setup right here. A centripetal force is keeping the rubber stoppers from going in a straight line. The centripetal force is always directed toward the center of the circle. It's tension in this case, provided by this weight right here. Now, if I were to cut that weight, those rubber stoppers will go flying in a straight line. Remember that the velocity that the rubber stoppers have is both linear and angular, meaning that they travel so many revolutions or so many radians per second, but they also travel so many meters per second. The angular velocity doesn't depend on the radius, but the linear velocity does. An important note about revolutions is that the axis is external. In other words, the rubber stoppers are going around my hand. In a rotation, the axis is internal. So they're actually all rotating about an internal fixed point. This setup right here is a setup involving rotation. Again, both of the pom-poms have the same angular velocity. They're sweeping through the same number of radians or revolutions in a given amount of time, but they have different linear velocities. So in this unit, we're going to learn to convert angular displacements to linear displacements, angular velocities to linear velocities, and angular accelerations to linear accelerations. We're also going to talk about what causes a rotation. See, a revolution is caused by a centripetal force, but a rotation is caused by a torque. Torque is what makes stuff rotate. Actually, more specifically, torque makes things have an angular acceleration, a change in their speed of rotation. So if something is rotating, it will keep rotating forever unless you put a torque on it. And if something's not rotating, it'll keep not rotating unless you put a torque on it. So if you want something to rotate faster or slower, you need to put a torque on it. The formula for torque is force times radius. And the assumption is that the force and the radius are perpendicular. So when I push on a door to open it, I push my force perpendicular to the radius that I am out from the door. Right? If I were to decide to have some kind of weird angle, it wouldn't work as well. I wouldn't be able to get as much torque. And it's only the component of my force that is perpendicular to the door that counts. So we say it is F cross R. The cross product means that you're taking the perpendicular components of two vectors and multiplying them. Or another formula is force times radius times the sine of the angle. So probably you've tried this before, but if you push on the door out here, it takes a really small force to accomplish rotation. But if you have a small radius and you want that same rotation, you're going to need a much bigger force. You have to push a lot harder. It's kind of silly to try to open the door in here. I think you probably heard the same thing when you're using a hammer before, that you don't really want to choke up on the hammer because leverage, that's another word for torque, means that we need to have a bigger radius and we can have a smaller force to get the same amount of leverage with the big radius. A lot of people use this idea when they're using a wrench and something is just too tight for them. You might be out on the end of the wrench and you still can't twist something, but if you use a cheater bar on your wrench, now you can apply just the tiniest little amount of force when you're way out there because you have so much more torque. However, not all things respond equally to torques. Oftentimes, the force trying to provide a torque on something is the object's weight. We can think of weight as a vector pointing from the center of mass of an object straight down towards the center of the earth. So why are some objects able to be stable and other objects topple? Well, if you look at this setup over here, I have a string kind of representing the weight vector from the center mass of the brick pointing straight down towards the center of the earth. And as I start increasing the angle, the risk of toppling gets greater because if you look at the weight vector, it starts to work its way where it's almost outside the support. We're still barely inside the support. As soon as you are outside the support, it topples. For this horse, when the legs are together, the center mass is behind the support. So it falls towards the back. But when the legs are apart and we're just resting on the back leg, the center mass is in front of the support, so it falls forward. So the horse can gallop down the ramp by having an adjustable support. Mousetrap cars can teach us a lot about rotation. We're using a lever arm here so that we can get the maximum amount of torque from the mousetrap. Then that is transferred to the axle with a string. The string is pulling on the axle with a small radius, so it's actually putting kind of a small torque on the axle. However, every time that the axle rotates, the tires rotate, and because the tires are much bigger than the axle, we can travel much further distance for one rotation. It's a careful balance between being able to get enough torque on the axle and being able to get enough speed by having the right ratio of wheel size to axle size. You should notice that we're getting an angular acceleration from the torque, meaning that the rate of rotation is picking up. Torque is about causing an angular acceleration, meaning that things rotate faster and faster as the torque is applied to them, or slower and slower as the torque is applied to them. So the mousetrap car's axle started rotating faster. That caused a linear acceleration for the car as well. Not all things respond equally to torques though. Some things do not like to change their state of rotation. We call that rotational inertia. So this red wand, I can put a torque on it to get it rotating, and then I could stop it like I just did and change its direction of rotation. And I can do it very easily. But if I use the blue wand, it fights against me because it doesn't like to change its state of rotation. It doesn't really want to start rotating, but then when it starts, it doesn't want to stop, and I always go beyond the vertical point. There's a big difference between these wands. They're the exact same mass, but the red wand has its weights really close to the center, and it's hollow on the end. The blue one is hollow in the center and has its weights on the end. The further out the weight is from the center of mass, the more inertia, rotational inertia something has, and the more that it resists an angular acceleration. So you have to put more torque on it just to get the same change in rotational speed. I have two spinners here, both with the same mass, but one of them has a small rotational inertia, the other one has a large rotational inertia. The small rotational inertia will be much easier to get spinning, but it will also be much easier for a torque from friction to bring it spinning to stop. I'll spin this one first. You can already start to see a difference in the rate of spinning. The one with the small rotational inertia is being affected much more by torques from friction. And it has already come to a stop. Here I have an apparatus where I can vary the rotational inertia. By moving these shaft collars in, I can reduce the rotational inertia, and using the same 200-gram mass, which is going to provide 1.96 newtons of force at this small radius, to get a torque, I will get different angular accelerations. Right now, I have moved the shaft collars in, and you're going to see a much bigger angular acceleration. And you also see a bigger linear acceleration. Objects that are rotating and moving along the surface have two kinds of kinetic energy. They have translational kinetic energy, and they have rotational kinetic energy. Translational, 1/2 mv squared, is just dependent on the mass and the speed of the center of mass with respect to the surface that it's moving along. The rotational kinetic energy is dependent on the rotational inertia, which is more concerned with how far out that mass is from the center and the angular velocity. So an object that has more rotational inertia is going to be harder to get moving when it rolls down a ramp. It will require more work because it needs to gain more rotational kinetic energy to achieve the same angular velocity. And the angular velocity at the bottom of the ramp is related to the linear velocity. Remember, you just take the angular velocity times the radius. So I'm going to show you how to know which shape object is going to win when rolling down a ramp. So first I have some marbles in a disc, and it's hard to tip it towards the camera, but it has the 4 marbles in the center of the disc versus this disc has the 4 marbles on the outside. So I'll be running the ones in the center furthest from the camera and the ones on the outside closest. I'm gonna shut these so that my marbles don't go flying away. All right, so according to our prediction, the one that has the mass close to the center should be easier to get moving and should get to the bottom of the ramp fastest. So I'm predicting the one over here on the right, where they're close to the center, will win the race. 1 for 1. Right, I can use that same principle when looking at shapes. So if I have a hollow cylinder or a hoop versus a disc, I would predict that the disc is going to win because the mass is closer to the center of mass with a disc. So I'm going to run the disc on the close side this time. Ready, go. You can see that the disc won. All right, well, what's even better than a disc? A sphere. Spheres have the least rotational inertia of any shape because you cannot get the mass any closer to the center of mass than with a sphere. So I'll run the sphere on the far side. Ready, go. Ooh, that's very close. But I do believe the sphere won. All right, what about if I were to compare a solid versus a liquid? Well, at first you might think the solid is going to do better because it seems like the mass is close to the center of mass. But liquids actually cheat because liquids do not actually rotate. They slide inside the container. So there's really no rotation going on for most of the mass. See, if you had a choice, rotate or don't rotate, if it wasn't for friction, you should always choose don't rotate. Think about this. In wintertime, you're going down a hill and you take your sled down the hill with very little friction, and somebody next to you is going to roll in a tractor tire down the hill. Your sled is going to beat them every time. The only reason that rolling is advantageous is because of friction. So the liquid, not having to worry about rotational kinetic energy, should be able to beat the solid easily.